In this second video on significant figures, we're left to interpret the recorded measurements of someone else. So someone has used an instrument to make a measurement, and we need to decide, were the digits that they wrote down significant digits, or are they more or less placeholders? Are they non-measured digits that are necessary but not actually significant? And we have several rules for this. Most of these rules are pretty easy to follow. Let's take a look. The first rule in reading a recorded measurement is this: anything that's not a zero must be significant. Someone must have measured it if they didn't write it down as a zero. So what we're going to find out when we apply all of the rules for reading recorded measurements is it is the zero that causes us the most problems, that causes the greatest decisions to be made. For the first rule, it's pretty simple. If it's not a zero, it is significant. So this first measurement of 345 has exactly three significant figures. Now remember, in any measurement, the last digit, I should really say in this case, the last non-zero digit, is a guess. And the digits that came before it are certain. But we know that those digits, all three of them, are significant. In 1278, there are four digits there. None of them are zero. So we would say four significant digits or four significant figures. 0.5676, this first zero, we're not sure about. We don't have a rule for zeros yet, so let's leave it out for now. The other four digits are not zero, and so we'll say for now, this is four significant digits or four significant figures. Last one is 2. Easy enough, right? The next rule is our first rule that involves zeros. We're looking at what are called trapped zeros. These are zeros that show up in between two significant digits, okay? Or in most cases, two non-zero digits, although there are exceptions to that. Anytime you have a trapped zero, it's understood that you measured the digit that came before it and the digit that came after it, and logic would tell us then that this digit also must have been measured. And therefore, we would say any trapped zero is a significant digit. 3045 has four digits, one trapped zero. This has four significant figures in it. 12,708, one trapped zero, five significant figures. 0.50676, one trapped zero, one zero that's not trapped. We still don't have a rule for that zero, so we're going to leave it out. So we're going to say that this is also five significant digits. 101,105, two trapped zeros in this case. All digits are considered to be measured and significant. So this has six significant figures. Our first two rules are pretty easy, but after that, it starts to get a little bit tricky. The next rule has to do with zeros that show up to the right of a decimal place, but it's even still more complicated than that. Rule 3 says zeros that are to the right of a non-zero and to the right of the decimal are significant. So this "and" is certainly the most important connecting word in that sentence. For a zero that follows the decimal, or for a zero that is following the decimal place, it also needs to follow a non-zero as well in order to be significant. So what I mean by that is 345.0. That zero is to the right of the decimal place, and it is to the right of a non-zero. It's to the right of 5 right there. And so we consider that zero to meet both qualifications, and therefore it's significant. 345.0 has 4 significant digits. 27.808. 27.808. This zero qualifies in 2 different rules. It's a trapped zero, so we all automatically know that it is significant. But that zero also is to the right of the decimal and to the right of a non-zero. It would also make it significant in that case. And so this is 5 significant figures. This next one is where people really begin to understand the rule fully. We still don't have a rule about this first zero, so let's leave it out. We've got 0.576000. When I ask students how many significant digits does this have, the first answer that I usually get is 4 significant digits. They count 5, 7, 6, and 0. They say the first zero is to the right of the decimal place and to the right of a non-zero, so they say it's 4 significant digits. They consider these zeros not to be to the right of a non-zero, but they are, right? It doesn't say directly to the right of a non-zero. It just says to the right of a non-zero. So all 3 zeros in this measurement, they're all 3 to the right of the decimal. All 3 are to the right of a non-zero. This is actually 6 significant figures. Lastly, 1.0, 111, 00, 150. All of my zeros are to the right of the decimal. All are to the right of a non-zero. This would have, let's count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant digits, if I've counted correctly. Everything's significant. And our final rule. This is where we first look at the idea of an assumed decimal place. Zeros that show magnitude only are not considered to be significant. What does magnitude mean? Well, let's take a look at the measurement 3,450. The first question I would ask is that zero an important number? Important is different than significant, but let's ask the question anyways. Here's how I'm going to tell. What if I just got rid of that zero and I wrote down 345? Would it be the same number? It's obviously not the same number. This is a number in the hundreds and not in the thousands. That's what we mean by magnitude, okay? Zeros that are at the end of a number before an assumed decimal place or to the left of an assumed decimal place are what we call placeholders. They're important because they show the magnitude, whether it be in the tens, the hundreds, the thousands, the 10,000s, etc. But we don't know if they were measured or not. They may just be placed there to show us where the decimal is. And so zeros like that are not considered to be measured digits and therefore are not considered to be significant digits. 3,450 only has 3 significant digits. Likewise, 10,780. The last zero is a placeholder. It shows us that this is a number in the 10,000s, and therefore it's not significant. It only has 4 significant digits. 250,000. We have 4 zeros at the end of the number. All are to the left of an assumed decimal place. All are showing us that this is a number in the hundreds of thousands. All are not considered to be significant. 250,000 only has 2 significant digits. And finally, let's look at the number 1 billion. 1 billion is a large number. We need a lot of zeros to show how large it actually is. But those zeros are only doing that. They only serve that function. This only has 1 significant digit. The same can be applied to numbers that are smaller than 1. We'll see that there are zeros that don't meet the qualifications posed by our last rule. Take a look at all 3 of these zeros. 2 of them are to the right of the decimal, but none of them are to the right of a non-zero. These are also placeholders. They just show us that we're in the thousandths place, but they're not measured digits. And so we say placeholders at the beginning of the number are not considered to be significant. This only has 2 significant figures. With 0.000490, the last 3 are significant. The first 4 zeros are placeholders, but look at that last 0. This 0 right here is to the right of the decimal, and it's to the right of a non-zero, so it's considered to be a measured digit. It is significant. Okay, so let's try some. Let's do some practice. Well, before practice, one last catch-all. Let's talk about scientific notation. Let's say I've got 3.45 times 10 to the third. I can to check significant digits, the only thing I have to do is look at the mantissa. All 3 of those digits are significant because they're all 3 non-zeros. Let's look at something like this, 5.400 times 10 to the fifth. I can ignore the power of 10. I just look at the mantissa. These zeros are to the right of the decimal and to the right of a non-zero. So this measurement has 4 significant figures. And the last one is kind of just a traditional rule. Sometimes you will actually measure zeros that might otherwise appear to be placeholders. If that happens, one of the things that we will do is actually show the decimal rather than mean for it to be assumed. So if I asked you how many significant digits are in 1,000 meters, these are just placeholders because they are to the left of an assumed decimal place. This only has 1 significant digit. But what if I actually measured those zeros and it was exactly or very close to 1,000 meters? One way I can express that and try to show that all of those zeros should be significant is by placing a decimal there. When I do that, I am making the assumption that I have measured those zeros, and just by showing that decimal, I now can say this has 4 significant figures. All right, some practice. 0.0010. The last 2 digits qualify. That last 0 is to the right of the decimal and to the right of a non-zero. This has 2 significant figures. 30,300. Those 3 are significant. The last 2 zeros are before the decimal place. They're placeholders. An interesting one, 20.00. These 2 zeros are to the right of the decimal. They're also to the right of a non-zero. That makes them significant. That also means that this 0 right here is trapped. So this actually has 4 significant figures. 0.010010. The last 5 digits are significant. The two zeros are trapped. We also have a zero at the end of the number that is to the right of the decimal and to the right of a non-zero. Significant, or I should say, scientific notation. Just look at the mantissa. This zero is to the right of the decimal and to the right of a non-zero. This is 4 significant figures. Finally, 20,200. Looks like it should only be 3, except for this decimal place is explicitly written. That's telling me that those zeros were measured, and so this is going to be 5 significant digits. That's a lot. We're going to practice this a bit more when we come back to class. Talk to you then.